Good afternoon, everyone. Just to thank you for taking the time out to just listen to this presentation. I'm going to be speaking on my use of Midas. And the main project I'll be speaking on is when I used it to design the White Bridge, which is a bridge in Scotland in 2017. Just before we start, I'm just gonna give a brief presentation, or a brief overview about myself, and then I'll give just a brief overview of about the bridge, why it was required, and then I will move on after that in discussing how we used Midas. So just to start with myself, I joined AECOM in 2012 as a graduate. I joined it when it was URS. I'm based mainly in Scotland, and over the last 8 years, I've been mainly involved in highway structures, so mainly highway bridges. Only started using Midas roughly 5 years ago, but this was on an intermittent basis, and over the last few years, I've got more comfortable in using it and been using it on a more regular basis. This project that we're looking at was the second structure that I ever used Midas on. And so within that, I'm just going to talk through some of the things that I've learned from that time, and just some of, hopefully things that will be of use and of benefit to yourselves. So just to start with, the White Bridge was a replacement bridge in the north of Scotland. This was commissioned by the Highland Council with AECOM as a designer and RJ McLeod as the contractor for the project. The bridge is 10 meters wide, and supports a single carriageway road. The main reason that the bridge was needed was as a replacement for an existing single arch bridge. The bridge that we're replacing is it was a single lane, so a 3.9 meter carriageway. Is a listed structure, and one of the main reasons that it needed to be replaced was there was a weight restriction placed on this bridge, as it was a main timber haulage route, and this restriction for the 18-ton basically necessitated the implementation of a new structure. So this is just an overview of the replacement. As you can see, so with the replacement, key things to note was we needed a new 40-meter span to cross over the river. Bridge abutment for this was a bank pad sitting on piles. The structural form was chosen to try and minimize some of the impact of flooding, as well as the road design. So an integral structure was chosen to comply with guidance from BD 57, which states that, used in the UK, which states that for structures not exceeding 60 meters and not exceeding a 30-degree skew, you have to have an integral structure, so no movement joints. And further to that, we also adopted weathering steel to minimize, again, issues with maintenance, as this is a bridge over water. So those are some of the main considerations that we're taking into account for the bridge. So shown here is just one of the bridge in its final state after it was finished. The bridge opened in May 2019 for a cost of just over 2.65 million pounds, and had the added benefit of improving access for all road users, so no more traffic light over the single lane that was a previous bridge, as well as just a continuous flow of traffic, and also importantly no weight restriction. So I'm now just gonna just start discussing how Midas was used on this project. So Midas was mainly used for the analysis and the design of the superstructure. The construction stages were modeled within Midas to take into account consideration of the construction sequence that we envisioned. Further to this, Midas was used primarily for the design of the main steelwork components, using the Midas design modules for steel design. This was mainly for the steel elements, so the bracing elements within the model, and then the other module used was for the composite design, so which deals mainly with BSE and 1994 Part 2. So the model was built with an anticipated construction anticipated construction sequence in mind. So the construction sequence that we had for the bridge following the technical approval process was you install the piles first, cast your pile cap over the piles, you land the beams, and then you pour the deck excluding the ends, and then finally at the end you make the deck integral. So a key aspect to this when you're using Midas is to make use of just the group function within the model. This is quite a powerful tool for helping you create a model where you're having to use construction stages. So the three main group functions that you have is one for the elements, one for the loads, and one for the boundaries. Shown here a few different groups that I created for this Whitebridge model. For the size of model that I had at the time, I think especially for the boundary group, most of the groups that are shown there were not strictly necessary. And the similar thing for the load groups, the groups that were created were not strictly necessary. These groups would only be of use when if they were to be included in the construction stage sequence. But as I said, this was one of the first models I was creating, so I wasn't fully familiar with some of these functions and how best to make use of them. The structure group model, the structure group element is quite useful within the construction stages, but is also quite useful just within navigating the model itself. It's a very good and easy way to just visualize specific elements of your structure. If you just want to look at the bracing, say, or any cross bracing and anything of that nature, if you just want to focus on those key aspects of your structure, then using the structure groups is quite a powerful tool that you have within the model to then model. You have to be able to see that aspect of your structure of your model. So I'm just gonna talk briefly next about the key things for defining construction stages and the application of this within my model. So when defining construction stages in Midas, this is done as a load. So if you go into load construction stage, and then after that a dialog box pops up for the construction stage. Once you click onto that, you're then able to add all the different construction stages that you have along with the duration time. So this is a dialog box that is visible to you when you click on the construction stages, and as you can see here, we're currently focused on the element aspect of just the element aspect of the model, and you can see all the different groups for the elements. Similarly, you can also see across you have boundary and load. So this is just a more expanded version of that, and within that you will see all the groups that you've created. As shown. So as again, this is for the elements, this one's for the boundaries, and this one's for your loads. So what's shown here is the first stage from my model where I'm activating for the elements, I'm activating my north and south abutment. This was just the power cap and the piles. I'll show that in my next model. In the second part, I'm activating my boundary group. So this is the springs and any other boundary conditions defined for the piles. And then I'm also activating the self weight. So shown here is stage one view of my model. And as I've explained, the elements that are shown are for the piles and the lower part of my bank pad, as well as boundary conditions being springs being activated for the piles. And lastly, the load is just gravity being activated. In the next stage, we've activated elements for the steel girder. The bracing elements are also activated. Along with this, for the boundaries, I'm activating the rigid links at the bracing locations, and also elastic links were used to create a simply supported condition that would exist at this stage prior to the integral connection being created. In this stage, there's no additional loading being applied to my structure. Since we've already applied gravity, the software is just able to automatically apply the gravity load to the steelwork, and so we'll be able to get the corresponding bending moments and other results from this stage if we need to. And the other thing to note with the steel elements, which I'll kind of briefly touch on later on for the composite beam, within the software you're able to it allows you to pick out the two components that make up your composite beam, so the concrete and the steel element. So for the composite element that you see here, for these ones here, all that's shown at the moment is the steelwork element, and the self weight is only taking into account the steelwork and not the added concrete. In this stage, we've added in wet concrete load. This has been loaded as a line element. Nothing else is activated in terms of any elements or boundaries, just the load group for wet concrete is being activated. And again, at this stage, the elements that are shown, the steel is still shown as just a steel element and is not incorporating any concrete sections into it. The next stage is the final stage that we use for the model. So within the elements, I've activated the rest of my bank pad. I've also activated the transverse members for my elements, so it's now a full grillage model. For the boundaries, all we've done here is deactivate the elastic link condition, so it's no longer simple supported, but instead the software will now take that as a fixed connection. For the loads, I've activated the superimposed dead load, which would include the surfacing, the parapet, and the concrete pavement. So just alluding back to what I was saying for the different elements for the steel, the software is able to pick up the two different parts that make up your main steel girder. So as you can see in the upper part is at stage 3, where if you're looking at the element view with it being fleshed out, all you have available to you is a steel girder. Whereas on the second part of your, the second part of the slide, the bottom part there, where it's stage 4, the top part of the element is now activated. So we now have the beam is essentially now composite for that view, where we have steel element and the concrete element together. So this, when you finish doing your construction stages and you're happy, one of the key things that you might want to do at this stage is just to run the analysis. During the construction stage element, depending on how you've activated your groups or your boundary conditions, this is a most likely place that you're going to have in terms of any mechanisms, or if there's any issues with your model such that you've not defined your loads correctly or anything else like that. It's a very useful point to be able to just to do, even like especially for this case where we have for the simple supported for the beam, you can do some simple hand calcs just to make sure that the numbers that are coming through are correct and you're happy with what's happening. In addition to this, one of the things that you can do as well as you go through the model is just do a few checks to see what's being activated. So shown here is the tree menu, which is visible on either left or right hand side of your Midas when you have it open. Within sort of the different stages, you can kind of see what's being activated and what's not. So key things to see here, you can see where you have all the blue sections highlighted, that those represent elements that are still to be activated. So in stage 1, all that's been activated is my pile, which you can kind of verify through the material element that's being activated. And then you can also see, so I've got the case pile being activated, which is one material, and another material for the lower part of my pile cap, which is got a different material strength. In addition to this, for the section, you can see I've already activated the case pile. And again, for the boundary conditions, we only have springs that are defined for the piles. And similarly for the self weight, there's only one load that's been applied. Whereas in contrast for stage 3, we now have a few more things activated. So even as an additional check within this, so I just move on to the next slide. As an additional check within this, you can see in stage 3 for the boundaries, like there's a few more things that have been activated. So as I mentioned before, elastic links, beam end releases were also used within the model. So these are key things that you can use as you progress in your model, just to make sure that the things that you're expecting to be activated are being activated, and the model is functioning as you would want it to. One of the useful features within the construction stages as you progress with your model is, I guess it's worth noting that when you add any load case or define any load within your construction stages, Midas automatically adds that as a cumulative load to the dead load. So if we have defined self weight and the wet concrete and anything else that comes after that, those loads will all be included within the dead load case, which may not be necessary or might not be ideal for what we're looking at, particularly if there's loads that we want to be able to manipulate later on in our design. So in this instance, one of the things that I did for my model was defining within the software was distinguishing loads that I wanted to have available to me in my post-construction, post-analysis stage. So within this, if you go into the analysis and construction stage, you have this dialog box which opens up, and within that you then have the option to be able to create to distinguish loads from dead load as is shown within the menu here. So yeah, shown here, the key loads that I distinguished was one for the wet concrete and the other one was for the SDL. And I wanted to have those loads available to me afterwards in my post-construction stages and within my load cases. So you can kind of see this is just a small window from the load combination dialog box when I'm now doing my load analysis. One of the main reasons that I wanted to do this as well, because we're dealing with two different materials, mainly steel and concrete for the concrete beam. When you come to doing your load combinations, to Eurocode, concrete and steel have two different load factors, and as a result of this, being able to distinguish, at least in my case here, I chose to keep the wet concrete load case activated throughout my throughout my analysis, and the wet concrete load was also used as to represent the weight for the concrete within the structure, and to be able to manipulate those two effects, one for the steel and one for the concrete, using the distinguishing load function meant that in my load combinations, I'm able to apply the 1.2 load factor for the dead load, which in this instance is just purely for the steel, and then I'm able to apply my 1.35 ULS load factor for the concrete, which in this instance was represented by the concrete. And similarly, where a combination requires SDL, I was able to then put in separate distinguishing load cases for that, even though this has been included within my my construction stages. But yeah, this is a very useful feature if you're using Midas, at least in terms of just allowing you to control what's happening with your model and being able to see different things further to this. Just other loading that was considered within the creator of this model. Obviously, as this is an integral bridge, we have the effects of strain ratcheting at the abutments. For this model, and just for my level of experience that I had at the time, not being able to use I think there's a function within Midas that is able to try and recreate some of the effects for strain ratcheting. We basically took the approach where we referred to PD6694 for creating to find the K-star coefficient for earth pressure loading. So the procedure that we followed is what was defined in clauses 944, 945, and 946, as well as Annex A of PD6694. This being a structure that is supported on a single row of piles, simply using the coefficients from PD6694 was not quite right. A bit of interaction was required between myself as a structural designer and the geotechnical engineers to come up with appropriate spring values for the piles, and also to an extent for the abutments and the coefficients that were applied for that. So once that was all defined, the loads for K-star were entered as a hydrostatic pressure within Midas, and then we also used multilinear springs for the piles. This was mainly to account for the different stiffness values that you would have under contraction and expansion, as the riverside has a slope that needed to be accounted for. The verification of the steel beams during construction, this was completed to BSc in 1993 Part 2, but was done as a hand calculation to find the critical moment and then calculate the buckling factor for the beams under the wet concrete load case. I'm aware within Midas, again, there's an option to use to create a 3D model where you might define the beams as plate elements, and through that be able to find your critical buckling factor under eigenvalue analysis. So shown here is just just a slide showing how the K-star load was applied, and again, this is through just if you're going to load static loads, there's a hydrostatic pressure function which allows you to apply your loads based on your graded intensity, and you just get a yeah, it does a quick calculation for you to get the effective stress on your plate elements. The key thing with this is that function is only available for plate elements and not line beams. And as I mentioned, the other thing that we used within Midas again was a multilinear function for to represent the springs for the piles. So you could, as you'll note here within this is just two different slopes for my springs, and this was mainly due to under expansion we would have a slightly higher slope in terms of the spring stiffness compared to the contraction where it was a bit shallower. Again, this is accounting for the fact that we had a slope in front of the wall, and this was also taken into consideration feedback that we'd received from the geotechnical engineers as to what was appropriate after, yeah, as I say, a bit of iteration between the two of us. So having discussed those main parts of the construction stages and just other loading considered, I'm just going to briefly touch on some of the other useful features within Midas, and specifically in this instance, looking at the long-term properties. Within BSEN 1994 Part 2, there's a clause which which allows you to use a slightly different modular ratio when you're taking into account effects for creep and shrinkage. The software has a useful function that allows you to define these properties and then following that, just be able to apply them to different load cases that you're looking at. So this is one of the functions that or at least that I chose to take advantage of. So when you're creating your elements for the longitudinal members, so this is your steel element with its composite section. Within the menu, it also has a section further below that allows you to then enter your long-term modular ratio value. So in this instance, I've chosen, or we've put in a long-term modular value for the creep. Ideally, we should have been putting one in for the shrinkage as well, but the two values were very close to each other that we just chose to use one value throughout the design, and in a sense, try and simplify what we were doing and from that perspective. So shown here, after you've put in those values, you can see Midas basically is able to then give you a table of your properties as you go through the different stages. So in the first one is the value when it's still only, so value before is just still only activated. The second part is the steel with the concrete element, but this is under short-term modular ratio. And the long-term one defines the long-term modular ratio, and the shrinkage one in this instance is 0. But again, that is due to the fact that we've chosen in this instance not to use that. But once you've defined your long-term properties and you've put in the two different stiffnesses, the software automatically creates a group for you. So this is a boundary group that is created by the software automatically. And to be able to apply that to your different load cases that you have, within the analysis component of the software, there's an option to use what's called a boundary change assignment. So the group that I was referring to earlier on that will be created is specifically, it's a section stiffness boundary condition that you've created. So within the software, once you get into the boundary change assignment, which is accessed as shown, once you get into that, you then have the option to create that as a boundary group combination, and through that you can then apply it to your different load cases. So you can see here I've just applied it to what I've considered to be my long-term properties, which was the wet concrete, the self-weight, the verge and the surfacing, and but yeah, we hadn't applied it specifically to the earth pressure values just because of the changing nature of that. But once you have that that option, yeah, once you get into analysis again, the software is then able to pick up those differences in terms of your section properties and provide you an analysis on that basis. So yeah, I'm now just going to briefly, just to kind of enter the last part of my presentation, where I'm just going to talk about the analysis and design elements that we considered in during the design of the structure. So one of the main things is when you're using Midas, and you're dealing with a large number of potential combinations, sometimes it may be easier to create this in a spreadsheet first and then paste into Midas once you have that defined. The key thing with this though is you need to create the load cases within Midas first, and then copy that table into Excel. The reasoning for doing this is it allows you to figure out how many your cell column positions for each individual load case, and which is quite a key factor for your analysis. Further to this, as you go through this part of the sort of creating your load combinations, you also have the option to distinguish loads between whether the serviceability or ULS analysis. This is quite important if you are using the design modules within the software. You'll note on the left-hand part of the screen that most of these combinations are created within the still design area. And the key reason for this is it then allows the software to pick up these combinations easily when we come to doing all the different analysis that we need to do. And within the different aspects of these things as well, you also have the option to specify whether the combination is adding to itself or if it's an envelope, and the software and you can then use these functions later on, at least for the different things that you might need to do. And if you're taking the option again to use the concrete design modules, then obviously you'd create your load cases within the concrete design aspect of your model. So as I said earlier, the two main elements that we used within the design of this structure was for the still design module and one for the composite design elements. I'm quickly just going to start to briefly discuss the still design module side of things, and then I'll end on the defining the composite aspects of it. So these are the two menus that you have available to you, and as you are using them, it's simply a case of just working your way down the list. In terms of, as you can see here, for the still design one, you start off with design code, any partial safety factors that you might want to consider beyond what is defined in the Eurocodes. And one of the ones that you can see as well is the one for serviceability load combination. So the software should, for the most part, pick up some of the, from the previous slide, it should pick up the code, the elements, so the combinations which are for SLS, but because it's Eurocodes specific, particularly for when you're doing concrete design, you might need to distinguish between if it's a characteristic combination or a frequent combination or quasi-permanent. So there's the function to do that within the software. One other aspect, when you're looking at still design, you have the option to either do a still code check or a still optimal design. So for the Whitebridge model, we chose to use a still code check. One of the reasons for this was considering the bolted connections that we had for our structure. We wanted to, and just consider that, and also what we thought was available to us in terms of material sections from just the different suppliers, at least that we got in touch with, or at least the catalogs that we viewed. We chose a specific section, and as a result, when we were doing the analysis, because we wanted to use a particular section, the still code check was a better option to go with for analysis. However, if you're not too worried about sort of the material size that you need to use, but you can also use a still optimal design where the software is just able to look at a whole host of section sizes and sort of suggest to you what you need to use. So shown here is just analysis or the output that comes from the still code check. This is a very quick verification that we're able to do for the still angles, the bracing that we used. As you can, as I was saying before, you can kind of see that most of the utilizations shown here are quite low, but again, the section that we chose was mainly due to availability and also just the connection detail and making sure we respected all the requirements of BS-EN 1993 Part 1, Part 8. But the software is clever enough to just go through all the different checks for your actual resistance bending and the combined checks that are required, as well as the shear, which in this instance was minimal since the bracing elements were being considered as truss elements, and there wouldn't be too big a shear component assigned to them. And yeah, lastly, this is the last part, which I'll discuss again, just the design of the steel girders, mainly in their composite state. So the module for composite design, once you get into sort of the different menu aspect of things, one of the first things that you can specify within the software is what you wanted to design for. So in here, I've kind of ticked off everything, which includes bending resistance, the vertical shear checks, as well as the two combinations shown on the right-hand side for the stress limitation and the longitudinal shear. There's separate checks that you would need to do for connections which are welded. So this is mainly if you're looking at your flange and your web. So that was done as a hand calculation. And similarly, where you have a splice, you would need to do this out with the software. And as I said earlier, for the verification of the steel during the construction stages, that was done externally through a hand calc. When you're using this particular module, it doesn't necessarily do the backlink checks on the steel, but the analysis and the results that you get from the static load cases are pulled through the model. And in addition to this, you need to specify the elements that you want to analyze. So this comes back to the group function that I was mentioning earlier on. One of the ways that you can optimize some of your analysis time and the other things that you're looking at is to use a group function, and it acts as an easy way for you to pick which elements you specifically want to look at. So from my model specifically, the main specific things that we wanted to look at was max bending in the middle of the beam and the max hogging at the ends. Conveniently for us, just because of how the structure was worked, we can kind of predict where the worst effects of the model were going to be. So you can kind of see here, I've kind of defined, this is the girder design group that I created, and these are the elements that I've highlighted, which the software is going to do the analysis for me on. So as I discussed earlier on, you can kind of just work your way again through the software, and you define different parameters, similar to what I mentioned for the steel design. And as you work your way down the menu, you have the option to add all different types of properties. So you add in your design materials. Again, for the steel, sometimes if you're using thicker steel sections, you might specify that you want a yield stress of 345 or 335 if you're using something over 60 mil thick. You can define your longitudinal reinforcement, which is quite important if you know that there's going to be cracking at the ends. And the elements that I was talking about before, the design position and also the design output, again, you can create specific groups where the design position could be for all the elements for the composite beam, but the position output could just be picked for the west areas. So I'm just going to briefly show you just a couple of the inputs that you might add for through the different sections. So shown here is the inputs that you're adding in for the shear connectors. So you would be defining how many connectors you have, the tensile strength that they have, and their diameter, and the software is the design is then able to the software is able to just to pick out those things, and when it's looking at those particular elements, it will pick out the worst loading that is on that element and use the design properties along with that. And similarly, you can also define elements based on springs within your model. So you do a separate calculation noting the spacing between springs. So in this case, referring to for my structure was the spacing between the bracings and in addition to that, adding in the specific spring stiffness for those bracing along with that as well. And once you've defined all those things, and you've run, so after you do all those things and you define all that, you then just click design, which the software will then sort of go through and do all those checks. And depending on what you've selected as what you want for the analysis, so as you can see here, we've got option for bending resistance, the vertical shear. Because I had this all ticked off at the beginning, I can now view results on that basis. So shown here is the results that are available for my ultimate bending. You can see in the first column here, the software is picking up the first column here, the software is picking up whether or not it's hogging or sagging that we're looking at. So negative being for the hogging load scenarios, and the positive being for where sagging is occurring. In addition to this, is then picking up what's the West load combination type in terms, the West load combination in terms of just the different loads that you may have defined. You can kind of see here, so all my load combinations were numbered, so 1, 2, I think we reached up to 50, and I could refer to my spreadsheet to figure out what specifically that load combination was. In addition to this, the software is also able to classify your section for the different scenario. So you'll note for the hogging load cases, my section for the most part is class 4, whereas in the sagging scenario, the section becomes class 1 because the compression flange in that scenario is being restrained by the concrete. So the software is picking that up, and then within this analysis where you're looking at MA, again, this first two, this is MA refers to your total loading before construction, and then MCED is your after construction loads. And yeah, further to this, you have then your resistant capacity, whether it's plastic, if it's your class 2 and above, or even if you're class 3 as well for a steel section. And then for a class 4 section, you have the output that the software is able to produce. And again, you can kind of just use that as a basis for, at least in the first instance, just checking that your results are okay. There's nothing wrong. If anything comes up in red, then you know that the section is not working, and you might need to just have a better look to figure out why that's failing, and you can look to try and optimize that element of the design. After you do this is after you've done this, you then have the option to print results. So again, if you specify that you want a particular element to be available as an output, the software, then you can print the result from that point, and you can see your different output values. So to start with, you can see the parameters that we defined specifically. I've put in a slightly lower steel property. So typically, would you have had 355 steel has been used, but because we're using slightly thicker steel flanges, I've just limited everything to 345, and these parameters up here as per the Eurocodes. So just from that, this table, basically you can just kind of work your way through it, and it is a design calculation that you can use for cross-checking and making sure that everything that you think is happening, and you can use that as a verification, as I was saying. So shown here is one of the outputs where for lateral torsional buckling, that the software is just been able to go through. As you can see, we had a 80% utilization, and there would be a check that would show that this is okay. And these are the design loads that have been entered in for that particular element, and the load combination that goes with this. So if you want to, you can again just go back and sort of do a quick check to verify these values, and also just to verify how the software is producing the buckling resistance. But this is at least a nice quick tool when you're looking at your beam design to be able to use and just see how the software, or at least how your section is doing. And if you're happy enough, it's an easy output that you can also include in your design calculations. And again, similarly, from what I'd shown you before, in terms of the inputs, this is the output that's been produced for longitudinal shear. Again, so in this scenario, a slightly different combination from the one before is a worst case. and the software again has gone through and picked up all the different analysis. You can see here I've provided more than enough shear studs for the analysis, and actually it's, yeah, quite underutilized in this scenario. But again, these are things that you're able to verify throughout, and yeah, just work your way through as you go through your different analysis. And I think this brings me to my last slide. So hopefully this has been of use to yourselves, and yeah, hopefully that this has been of use and you found this quite good for what you need. And hope if you have any questions, I think just let me know. Kind of just see if I think there's a question in here.